Welcome to part 2 of the science of the GCBM. In this video we'll be continuing from where we left off in part 1 and move on to a discussion of landscape level carbon stock dynamics, output indicators, and carbon pool initialization, or spin-up. Let's start with landscape level carbon stock dynamics. Fundamentally, the model is a giant bookkeeping tool that tracks for each stand the ecosystem carbon dynamics over time. Displayed here is just a simple total ecosystem carbon density curve. After a disturbance, dead organic matter pools decline, and eventually, the rate of regrowth exceeds the rate of carbon losses, and the ecosystem carbon pools begin to increase again. At the landscape scale, you also have an age-class structure, so we'll keep it simple here and assume that every stand on our landscape is growing on the same yield curve, but some stands fall into different age classes, so 0 to 20, 20 to 40, and 40 to 60, for example. And there's a specific amount of area within each age class, so if I want to know how much carbon I have on the landscape, I simply multiply the area in each age class by its carbon content per hectare and obtain the carbon content for the age class. And then sum up the results for each age class to obtain the total carbon for the landscape. This basically sums up what the model does at the beginning of each time step. Where things get a little tricky and interesting is how the model deals with landscape level dynamics. The model basically represents the population of all the stands in a project inventory. So in this example, if we have a normal forest where 1% of the forest has been harvested every year for a long time, we end up with an equal amount of area in each age class. When the oldest age class is harvested, the area is basically moved from the oldest age class to the youngest age class, and then it starts to regrow. What that means, assuming a constant disturbance regime, is that what is the youngest age class is what was disturbed in the last 20 years. This means that the sum of the area disturbed in the last 20 years is equivalent to the sum of the area in the youngest age class, assuming no land use changes, regeneration delays, etc. If there is a change in disturbance rate, for example, the harvested area is cut in half, two things will happen. First, the amount that was added to the youngest age class will be half, in this example, 10 hectares, and everything else has gotten older, including the 10 hectares left over in the oldest age class, which now moves up to a new age class. So the area contained in one age class has been split between two, that which was disturbed in the last 20 years and that which was allowed to continue to grow. In the previous slides, we described how to calculate the total ecosystem carbon stocks on the landscape. But what we can see here is that if there are disturbance events that change the age class structure, meaning a change in disturbance regimes, you also get a change in carbon stocks, and whether that area is acting as a carbon source or a carbon sink. In this example, there's an increase in disturbance rates, so relative to the example below it, the one above has more disturbance. And typically, that means there is a shift in the age class structure to younger forests and, on average, a lower carbon content. This transition due to more disturbances usually means the landscape is a carbon source during the transition. And conversely, if there is a reduction in disturbances, that is, more of the forest is allowed to age into the next age class, you obtain an overall increase in the average forest age, resulting in a higher carbon content on average. And the transition from the middle landscape to the lower landscape results in the landscape acting as a carbon sink during the transition. This brings about a very important concept called the age class legacy. What it effectively means is that the future carbon stock changes in a landscape will be affected by the current age class structure of the managed forest, which is the result of the past changes in the disturbance regimes. The legacy means that you can have old or young forests that have very different carbon uptake potentials in the future. For example, if your whole landscape is full of old forests, without disturbances, the ability of that old forest to sequester additional carbon is very small, whereas if you have a landscape with much younger forests, the ability to sequester more carbon is high. But what happened during the transition also matters, that is, how you got from old forest to young, and what happened to the carbon. For example, was it burned? Was it harvested and used for bioenergy? Was it put into long-lived forest products, etc.? And this will have a big impact on the dynamics. The model keeps track of all the carbon stocks, areas, and carbon fluxes, transfers of carbon between pools. What are generated as outputs are carbon stocks and stock changes for user-specified areas over user-specified time periods. Earlier in the presentation, stand classifiers were discussed, and if the user wants to filter results by region, for example, a classifier and classifier values for region should be included in the user's stand classifier sets. This kind of classifier would not be used by the model for any other purpose than to identify stands and for the user to filter results. Stand classifiers serve four main purposes: to identify a specific inventory record, to identify the related yield curve, to aid the selection of stands for disturbance events and transition rules, and to filter results. The model generates a wide range of output indicators for a simulation in both spatial layers and a database, which can be queried to obtain results for all of the biomass and dead organic matter carbon stock pools, how much area was affected by management and disturbances, the age class distribution, and how much carbon was transferred to the forest product sector or to the atmosphere. And you can trace back where the carbon came from, which pool, which gas, and due to which disturbance. If the user wants to dig deeper than the standard set of indicators, they can develop their own SQL queries and query the results database directly. A number of scientific indicators are generated in the results, including annual litter fall, the rate of decomposition release by dead organic matter pool, as well as net primary productivity, net ecosystem productivity, and net biome productivity. NPP is simply the difference between photosynthesis and respiration, that is, the amount of organic matter produced in a time step for a specific area. It should also be pointed out that the model does not explicitly simulate photosynthesis and autotrophic respiration. It uses the user-defined yield curve, which defines how much increment occurs in the woody biomass, and then it calculates the increment in the production of other dead organic matter pools, including fine roots, to estimate the net primary production. If you subtract heterotrophic respiration or decomposition from NPP, you obtain net ecosystem production. This is the equivalent to net ecosystem exchange obtained from flex towers, although the sign is reversed. So in the model, a positive NEP value suggests a gain in carbon stocks. And finally, if you subtract carbon losses from disturbances from NEP, you obtain net biome production. In conclusion, the GCBM is a modeling framework that can be applied at the stand and landscape scale. It incorporates the best available science, and it will continue to be updated by the Canadian Forest Service Carbon Accounting Team as the science evolves. The model is compliant with IPCC guidelines, including having the ability to parse out results between naturally disturbed versus anthropogenically disturbed forest stands. And the Canadian regional parameters will also continue to be updated by the Canadian Forest Service Carbon Accounting Team as required. The last topic of this presentation is explaining how the initial conditions are created in the GCBM project. This is an important topic because most users typically have more data on the biomass dynamics of their forests than they do on the dead organic matter and soil carbon dynamics. This is slowly changing, however, most inventories do not contain data on dead organic matter. What we understand is that stand conditions and the disturbance history determine the current dead organic matter pool sizes. This is an important concept because many process and carbon models, based on processes, basically run a carbon model to equilibrium. That is, they assume that the stand grows for thousands of years with no disturbances, and then they take those pool values as the initial pool values for the simulation. Obviously, what that does is create oversized pools because dead organic matter and soil carbon do not accumulate indefinitely over thousands of years. Disturbances occur in stands in some parts of the country every few years, every few decades, and in some much longer periods. So the assumption of running a process model to equilibrium always yields initial dead organic matter carbon pools that are too large. And if you start a simulation with these oversized pools on your landscape and then begin applying disturbances and management activities, all the dead organic matter pools will be driven down, not because that's what's happening in the field, but because the model overestimated the initial pool sizes. What the GCBM does, similar to MakeList in the CBM CFS3, is it has a spin-up process. That is, it spins up the dead organic matter pools, and it uses the parameters of the GCBM, unless the user configures it not to. The user provides the model with a forced inventory, but for each stand, they also must identify a historic and last disturbance type, and then the model can begin the spin-up process of generating the dead organic matter pools. The way the model does all of this is, for each stand in the inventory, it simulates repeated cycles of growth followed by the identified historic stand replacing disturbance, which is typically wildfire in much of Canada. Then, the model tracks the cycle of the carbon pools between iterations of growth and disturbance, and when the slow carbon pool values between iterations are within 0.1%, the model grows the stand for another iteration, but then disturbs it with the user-defined last stand replacing disturbance type, after which the stand is grown to the inventory age defined by the user. For example, if the historic disturbance type for a 30-year-old white spruce stand in the user's inventory was wildfire, and the last disturbance type was clear-cut harvest, The model will spin up the biomass and dead organic matter pools through the repeated iterations of growth and disturbance with wildfire, and once the slow carbon pool values are within 0.1% between iterations, the stand will be grown again and replaced with the clear-cut harvesting disturbance, and then grown to the inventory age of 30 on its defined growth curve. Thus, the biomass and dead organic matter carbon stocks of this 30-year-old white spruce stand will be properly reflected in the results in time step 0, the start of the simulation. The benefit of this approach is that it reflects in the initial conditions the past disturbances, and as the stand grows from age 30 to 31, there are no modeling artifacts. Presented here is just a visual example of the spin-up process in terms of the slow carbon pool, and it shows the repeated cycles of growth and disturbance until the values between iterations reach 0.1% of each other, at which point the stand is regrown and the user-defined last stand replacing disturbance type is applied. Users should note that the historic and last disturbance types assigned to each stand should be stand replacing. The user also has the option to indicate more than one last stand replacing disturbance and modify the default natural stand replacing disturbance interval, that is the year of disturbance for each. Some factors affecting the size of the slow dead organic matter pools of a stand include site productivity, because more productive stands produce more biomass and more organic matter, the mean annual temperature and associated decay rates. For example, a low productivity stand in a cold environment may still accumulate very large, deep organic layers. The disturbance regime, the historic disturbance type, and the natural stand replacing disturbance interval used by the spin-up process. For example, a jack pine site in the Boreal Plains ecozone might have a short fire return interval, and as such, smaller dead organic matter pools than a Douglas fir stand in the wetter Pacific Maritime ecozone that will have a much longer natural stand replacing disturbance interval. And, as has been previously discussed, different disturbance types in the model will have an influence on the transfers of carbon, so the choice of historic stand replacing disturbance type to be applied during the spin-up has an influence on the initial carbon stocks. As well, the selection of the last stand replacing disturbance type for each stand to be applied by the spin-up will also influence the initial carbon stocks for each stand. So, the spin-up process is basically the GCBM in a different mode, using the same code, parameters, and data for volume to biomass conversion for inventory, etc., but it uses the historic and last stand replacing disturbances and stand replacing disturbance interval for your regions. With that, the initial conditions are created. Unless you want to conduct a research experiment on climate change or some other aspect, you should use the same parameters to create the initial conditions as are used for the subsequent GCBM simulation. So, how well does this work? The CFS Carbon Accounting team published a paper in 2014 that involved a massive undertaking and 5 years of work that involved running the CBM CFS3, which the GCBM is based on, against approximately 600 national forest inventory plots, and the result was a mean bias for total ecosystem carbon of about 0.9% of observed values, almost exact. This was the good news. The bad news was that once the results were parsed into ecosystem types or pools, quite a few compensating errors were observed. It was found that the model tends to underestimate deep organic soils, and this led the team to develop a moss module and carbon model for peatlands that will be connected to a future version of the GCBM. This concludes the science of the GCBM. Thanks for watching, and feel free to subscribe to the channel to be notified about new content as it becomes available.